Hello everyone and welcome to another episode of the Power Logic. So today we're going to be doing the problem 13 of the 2022 Aime Ii. Now this is approaching to an end of 2022 Aime and the problems are getting significantly harder as shown in this expression, which seems to be really intimidating. There's a polynomial p of x with integer coefficients such that p of x is equal to this giant monstrous quantity, and it holds for every 0 is less than x is less than 1. Now find the coefficient of p of x to the 2022 and p of x. Now this problem seems to be kind of interesting. Want to find this coefficient, but this one we don't really know how to expand it because we have this on the top. But how are we going to even handle this monstrous expression in the bottom? Now let's look at Now let's try to closely examine this expression. So all of the term can be expressed as x to the m minus 1. This expression seems to be kind of interesting. Now let's also look at the number 2310. So 2310, this is equal to 21 times 110. 3 times 7 times 22, which this is equal to 3 times 7 times 22 times 5. 2 times 3 times 5 times 7 times 11. This is the expansion of 2310. Interesting. Now let's look at all of these numbers. 105, 70, 42, and 30. Now 105 is equal to 3 times 5 times 7. 70 is 2 times 5 times 7. 42 is 2 times 3 times 7. And 30 is 2 times 3 times 5. Okay, so now let's look at all of the prime factorizations. These are all divisors of 2310. So this kind of gives us an idea on how to possibly simplify this. Now we're going to go to an important identity. So first, we're going to try to examine what is going to happen if we divide x to the kn minus 1 over, well, let's say x to the a minus 1 over x to the b minus 1. If b is a factor of a. So now let's first try some terms. So without the loss of generality, let x be equal to 2 and let x be equal to 2. Then then we have 2 to the a minus 1, 2 to the b minus 1. So now let's say if a is equal to, so if a is equal to 3, b is equal to 1, then this is obviously true since 2q minus 1 over 2 minus 1 is equal to 7. So what if a is equal to 4 and b is equal to 2? 4 is obviously a multiple of 2. So this gives us 2 to the 4 minus 1 over 2 squared minus 1. 3 over 15 over 3. That is equal to 5. And a is equal to, let's try some more, 6. B is equal to 3. Then 2 to the 6 minus 1 over 2q minus 1 is equal to 63 over 7, which is 9. These are all integers, and we have been using our constraint that a is a multiple of b. Now we can kind of see a pattern, which is this seems to be true. This guess seems to be true. So now let's try to actually prove it rigorously. So we're going to proceed with a claim. So x to the b minus 1 is divisible by x to the a minus 1 is divisible by x to b minus 1 if b is a factor of a. So now we're going to write our proof. We're going to prove by induction. So induction is a really powerful technique in mathematics proof. So induction, you can just visualize it as a domino game. So we have a bunch of blocks, and now if I push this, the first block, then everything behind it is going to just fall down. So this is actually the same mechanism as induction. We just want to first show the base case. Now if x works, then x plus 1 also work. So this is actually so this second part is a general case. Whenever x as a variable works, then x plus 1 works. So this basically shows that the base case, the first block, is pushed down, and whenever x falls, then x plus 1 also falls. So this can just be shown to prove all integers and all positive integers, and b and a are obviously positive integers, so induction will be the best technique to prove this claim. So first, the base case would be when a is equal to 1 and b is equal to 1. Well, now base case is when a is equal to 1, b is equal to 1, then this is equal to 1, which is a trivial claim. Now we're going to deal with the inductive step. So inductive step is, now assume that x to the a minus 1 this is equal to m for an integer m. Now since this one is true, then what if we make it to be x to the k plus 1? So x to the ka minus 1, this is equal to m times x to the a minus 1. Now let's look at what is the relationship between x to the ka's power and x to the k plus 1 a. Now, this one we're just essentially adding now we're going to plus x to the k plus 1 times a minus x to the ka. Now, this is essentially the same as x to the ka minus 1. No, wait, x to the k plus 1 times a minus 1. Well, because these two terms essentially just cancels out. Since we add the same term and add the same term and subtract the same term, then we're going to get the same result. So now, this one is an integer. No, this one's an integer multiple of x to the a minus 1 from our claim. Then we just want to show that this term, that this part is going to be divisible by x to the a minus 1. And this is actually trivial to show because x to the k plus 1 times a minus x to the ka's power, this is equal to x to the ka to the a minus x to the ka. Now we can just factor this term out. Wait, excuse me for this part. So this one is x to the ka times x to the a. So factor this out, we're going to get x to the k's power times x to the a's power minus 1. And this is essentially x to the ka. X to the ka this x to the ka minus 1. No, x to the a minus 1. So therefore, our proof is essentially just complete. Because we already showed that this part is a multiple of x to the a minus 1. So for all integers k and a, then this one would actually be true. So now, how do we proceed to this problem if right after we prove this claim? Now we can actually just divide the entire thing. So we're going to get this entire expression. So now we can just take 4 of x to the 2310th power minus 1. Then this one just essentially gives us this multiplied by these in the same fashion. Now, is there a closed form of x to the kn minus 1 over x minus 1? Now, this one we have to make induction, using induction as our best friend again. So we claim that x to the kn minus 1 over x to the n minus 1 is equal to 1 plus x to the n plus dot 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 plus x to the k minus 1 times n. Now we're just going to prove by induction again. So the base case is when k is equal to 1. Well, and this one's essentially true since 1. Since when we divide the same number by itself, we're going to get 1, which was just our base case. So true. Now, inductive step. Now, from our previous claim, whenever we divide the new term here by itself, by x to the a minus 1, we're going to get x to the ka. So basically, for every time, we're just going to add a new term, which is x to the ka. When we divide x to the k plus 1, a's power, minus x to the k's power, from our claim that we just proved right here. So therefore, I'm just going to rewrite it right here again. Then plus, x to the k plus 1, a minus x to the ka over x to the a minus 1. Now, the left part by our claim is going to be equal to 1 plus x 1 plus xa plus dot 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 plus x to the k minus 1 times a. Now plus the right side. So right side, remember we just factored this out. Well, this just 1. So this just completes our proof. So now, from this proof, this entire expression will just be simplified into x to the 2310 minus 1 over x to the 105 minus 1 times times x to the 2310 minus 1 over x to the 70 minus 1 times x to the 2310 minus 1 over x to the 42's power minus 1 times x to the 2310 minus 1 over x to the 30 minus 1 and multiply it by x to the 2310 minus 1 square. Now we want to look back to our problem statement again. This number is less than 2310. So therefore, we just don't even care about these two terms. We just want to find the coefficient of x to the 2022 among this entire product. So from now, we just simplify these expressions from what we just proved. So the first expression, this one is just equal to 1 plus x plus 1 plus x to the 105 plus dot 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 plus x to the 105 times 2310 divided by 105. Now coming back to this, coming back to the prime factorization, we just get that this is going to be 22 minus 1. So just 21. So let me group all of these. Now this part is going to be 1 plus x to the 70 plus dot 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 plus x to the 32 times 70. Now we're going to continue our and this part is just equal to 1 plus x to the 42 plus dot 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 plus x to the 54. Now finally, the last series of terms is 1 plus x to the 30 plus dot 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 plus x to the 76 times 30. Now you can see that we want x to the 105a plus 70b plus 42c plus 30d be equal to x to the 2022. Because whenever we multiply, then any term in this thing is going to be expressed as x to the 105a. And same works for all of these. So now we can just rewrite this as the number of ordered pairs of A, B, C, D that satisfies 105A plus 70B plus 42C plus 30D is equal to 2022. Now, how are we going to proceed to this problem? So first, let's take both expression mod 3. Now, from mod 3, we can see that this is actually 0 mod 3, and and 70 is 1 mod 3, and both of these are all 0 mod 3 because 105, 42, and 30 are all divisible by 3. So for mod 3, we're just going to get B is congruent to 0 mod 3. So B is going to be divisible by 3. Now we're going to do a substitution. Let B be equal to 3k. Then this expression becomes 105a plus 210k plus 42c plus 30d. Now we also know that a must be divisible by 2. So a is also 2x plus 1. Now what about c? C, we can actually take this entire thing mod 5. Then we're going to get 2c is congruent to 2 mod 5, which c is congruent to 1 mod 5. Or technically, c can also be congruent to 3 mod 5. Now what about d? So d is actually, we're going to take everything mod 7. They're going to get 2d. Well, it's actually going to be 222 mod 7. So it's actually 6 mod 7. Now we're going to get 3 mod 7 works, and I think that is it. So 3 mod 7. So now let's just do all the substitutions. So this is actually 105 times, this entire expression just simplifies to 105 times 2x plus 1 plus 70 times 3k plus 42 times 5c plus 1, or actually also possibly 5c plus 3. Now we're going to add it to plus 30 times 7d plus times 7y plus 3. So there are actually two cases, and we're going to do one by one. So this is actually 210 x plus k plus y plus z plus 105 plus 42 plus 90, and that is equal to 2022. So divide, we're going to get 210 x plus k plus y plus z is equal to 2022 minus 150 minus 4 minus 42 minus 90. So if I didn't make any calculation mistakes, then it's 2022 minus 237. So x plus y, k plus y plus z is equal to 2 minus 237 over 210. However, this seems to not be a multiple of... Yeah, this seems to not be a multiple of 10. So let's check our calculation one more time. So b is a multiple of 3, and a is... Wait, sorry about that, but a is actually odd. So we're just going to get rid of this part. So we're going to subtract 132 from 2022. And this gives 2022 minus 132 over 2010. And this is 132 over 200. No, 1890 over 210. That's equal to 9. So I'm going to find the sum of number of ordered pairs x, k, y, z, and they're actually not limited to positive integers. They can be 0. So by stars and bars, then this is just 9 plus 4 minus 1, choose 4 minus 1, which is 12 times 11 times 10 over 3 times 2 times 1, which is 220. Now let's look at the case when this is actually 3 mod 5. Now, if this is 3 mod 5, then this is actually not going to satisfy, because, if this is 3 mod 5, then we're going to subtract by something that ends in 6. which is obviously not what we wanted. So let me just go back. Wait, 2c is 2 mod 5, so c cannot be 3 mod 5. Sorry about that, but yeah, c can only be 1 mod 5, so this by stars and bars, this just end our problem. So our answer to this problem is just 220, and we're finally done with this such long problem. Thank you for watching, hope you enjoyed, and I would catch you in the next